Okay, in the second part of the lab, we will create this circuit, a first order RC filter, a bit more advanced RC circuit, a little bit more advanced and complex than the first one. So we will again design a circuit, again with a time constant of 0.1 millisecond. However, we cannot use the values we picked for the previous circuit because now we have two resistors connected in parallel. Now let me explain what that means. Now, there's a shortcut to find the time constant for an RC circuit. If we have this circuit, to find the time constant, we can eliminate all the power sources, which means if it's a voltage source, we can short circuit it. And find the equivalent resistance between the terminals that the capacitor is connected. Now, what does that mean? Let's redraw this here. This voltage source is short-circuited. And these are the terminals that the capacitor is connected. There we go. Now, as you can see, R1 and R2 are in parallel, which means the equivalent resistance is equal to R1 parallel R2. And our tau will be this equivalent resistance times our capacitance. Okay, so the file says that this should be 0.1 as well. In the previous part, we used a capacitor with 0.01 nanofarad and 10 kilo ohm resistor. Now, in order to get a 10 kilo ohm resistor for the equivalent resistance, we need to use two 20 kilo ohm resistors, right? When you put them in parallel, the equivalent resistance will be 10 kilo ohm. However, we don't have a 20 kilo ohm resistors. So we can, sorry, one sec. Yes, we can keep using 10 kilo ohm resistors, but when we put two 10 kilo ohm resistors in parallel, we will get five kilo ohm, right? However, we still need a 0.1 time constant, so fortunately we have approximately 0.02 microfarad capacitors, so we can say 2 times 8, 5 times. So when we multiply these two values, we get 10 times. 10 times 10 to the minus 5, which is minus 4, which is equal to 0.1 milliseconds. I forgot to write milliseconds here. Right? So we can use two 10K resistors for R1 and R2. Let me write them here. And 0.2 microfarad for the capacitor. Now let's create our circuit with these values. Now we already have our circuit from the previous part. Now let's unplug the channel. We're going to plug it in later. So this was our previous circuit. We will just add a new 10K resistor in parallel to the capacitor. Let me take it. Let's put it here. And of course, we need to change the current capacitor with the 0.02 microfarad capacitors. So let's unplug this as well. And get one of these. These are kind of small, so right. And let's put this resistor here and ground it here. Okay. Now our circuit is ready. And we will observe VC, the voltage across the capacitor. So let's plug in our channel. Now we will plug the pins here and here. Let me zoom in a little bit. Okay, our channel is plugged in here and here, so we can measure the voltage across the capacitor. All right, let's go back to waveforms and yeah, we keep the same waveform, the square wave with 5-fold amplitude and 2 millisecond period. All right, let's go to our scope and run. All right. Okay, so here we have our waveform of the CV, the capacitor voltage. Let's stop it at a given point and see how it behaves. Again, it starts to charge up at the start of a given period, and it charges up to a value of roughly 2.68, which is, lower than the previous part, as you're supposed to find in your calculations. Let's keep running. And get our data within a given period, and let's export it. All right. So we have VC2. You need to compare this with your theoretical results, theoretical plot, and you also need to answer, you need to compare the waveform of the capacitor of this circuit with the capacitor voltage of the previous one. Comment on the differences, and you should also state which one is in more agreement with the theory and practice, and if you have any idea why.